Okay, so let's start. Welcome everyone. Welcome to week 6 of Data Science for Engineers problem solving sessions from NPTEL. I'm your TA, Saradi Pravalika. I'm a PhD scholar and a Prime Minister Research Fellow from the Indian Institute of Science. So, before we begin, I would like to lay out some instructions for you. So, this session is being recorded, and 3 to 5 minutes break will be given every half an hour or 1 hour. And if you would like me to cover any more topics, you can absolutely let me know beforehand so that I can prepare it well before, and yeah, I can discuss with you. And be respectful towards me and towards everyone else in the chat box and everything. And if you are being disrespectful, I will obviously remove you from the thing. And also, today is the last day for exam registration. And if you haven't done it yet, please do. Okay. So let's get started with today's topic. So today we'll be discussing about regression and ordinary least square, testing the goodness of fit of a model and hypothesis testing, right? So, and also I would cover some R codes for you guys for each of these topics. And also R code will not be there. Like specifically, we will not ask you to code anything in the exam. So, but here and there, some of the questions might be there, as you can see in your assignment problems. In the similar way, you can also find in the exam, but we will not ask you to code the entire thing or everything that I'll show today in this session. Okay, but everything which is taught in the lectures are completely useful. Okay, so let's get started. So, from the last week, from the introduction to data science, so I have uh, briefly told you about what supervised learning is and what unsupervised learning is, right? So, just as a quick recap, so supervised learning has some kind of an output, like a specific output, like a number or a class name or something like that. But whereas when it comes to an unsupervised learning, you don't have a specific output, but rather you have something called as a patterns, or you're grouping something, or you're categorizing some data and things like that. Okay, so today briefly we'll be covering regression, and regression is a kind of a supervised learning. I'll give you a brief introduction what supervised learning is, and then we'll go to regression. Okay, so so supervised learning, as I was telling earlier, you have some kind of an output, right? So in supervised learning, you have two kinds. One is regression and another one is classification. And there are many other types also, but these two are like kind of a bit famous. Okay. So regression is a kind of a problem that has continuous output values. Okay. So for example, let me say that I will take in some variables into consideration. Let us say you are owning a store. Okay. It is some time around a festival. Let's say New Year or or a New Year or something. So for New Year party, what do you guys do? So you will get a cake, you will buy some decorations and all of that. And when you have a store, you have to calculate, okay, given this month, I will need these many things, and this might be my revenue. So I'll take in some inputs, such as what is the month, so what kind of things I have in my store, and I will output what will be my revenue, right? So that is a kind of a regression problem. So some inputs you're taking and you're giving an output, like maybe say I'll have a revenue of 20,000 per day. Okay, so that 20,000 is an output value. You have a number. So it will vary for every day or every month and things like that. So it is a continuous output values. Okay. So if you're taking a classification problem, classification is like you're categorizing the output. So for example, hmm, what examples can we take? Okay. So if you are having some, okay, that is too much. You let us say you want to classify um, okay, some standard values. That's again. Okay, so classification, the easiest one which we can say, given a thing, classifying some pictures into cats and dogs. That is the most easiest one. right? I'll show you a picture. It can be a cat or a dog, and you have to classify it. Yes, this belongs to a cat class. It belongs to a dog class. So that can be an example of a classification, right? And we can represent all of this in terms of mathematical functions, which is y is equal to f of x1, x2, so on, plus some error. Correct. That means, let us say I have a black box. Okay, let's call this a black box, and that is denoted by f. I'm giving some inputs. These inputs are x1, x2, so on till xp. Some random features I'm giving as an input. And then I'll have some kind of an output, which I say it as y. Okay. So these inputs x1, x2, xp, they have multiple names. They are also called as predictors. They are also called as features. They are called as variables, factors. They have multiple names. Okay. So these x1 to xp, all of them are different inputs that you're giving to a black box. And that black box is doing some kind of uh, maybe mathematical functions, or it is processing something, and it is going to give you some kind of an output. Okay. So sometimes there might be prone to error as well. So we take an epsilon into consideration. So this epsilon here is an error. So this whole thing, if I write into a mathematical expression, it's this. Y is equal to f of x1, x2 till xp plus epsilon, right? So the main goal is to find what this f is. So we have two kinds, okay? One is prediction. So based on x values, we are predicting what y is. That is one type. And the second, black box can be anything. It can be a mathematical function, or it can be a machine learning model, or any kind of a thing that is taking some inputs and it is giving you some output. Black boxes, you don't know what exactly is happening in between. Okay. So to find this, there are two types. One is prediction and the other one is inference. So prediction is, given all these x values, you are getting some output as y. Okay, you're predicting y. We'll see some examples in the next part. Then you will understand this prediction part clearly. Okay. And the second one is inference. Inference is how y is depending on x. Okay. So in case if I'm saying there is a disease, okay, and what causes that disease? Okay. Let us say one of the reasons is common cold. Okay. From cold and body pains, I say these are my X values, body pains and cold and all of that. And Y is some kind of a problem. Let us say dengue or something. Okay. If I have to say, how is this body pains and this other cold and all of that is depending, like based on these two things, how am I saying that this person has dengue or not? So when you go to a doctor, you will lay out all your problems, right? And the doctor will give you some prediction. He will, based on your X values, I mean, based on your symptoms that you're having, the doctor will give you like, okay, based on all of this, I can say this is your problem. Okay, so that is a kind of an inference. Okay, so let's start with regression. In today's class, we'll be talking completely about regression only. Okay, so regression is a supervised learning. I have covered that a bit in the last slide. And that builds functional relationships between some dependent variables and independent variables. Okay, so again, the example of a doctor, if we take, you will lay out all your symptoms. Okay, so those are independent variables. And based on these symptoms that you're giving, the doctor will tell you this is your problem. That is a dependent variable. So the prediction that the doctor is making is completely depending on the symptoms that you're telling, right? So we have this dependent and the independent variables. So that is one kind of an example. If you want another kind of an example, it is the property rent price. So based on what kind of a property that you're having, so let us say you have a house, okay, you have some X number of square feet, and then you have maybe like it's a 4 BHK, and let's say there are like two balconies, it has like in private terrace and all of that. So taking all of these things into consideration, if you go to a real estate agent, he will tell you yes, based on all of these features that you're having in your home, I can tell you can sell your house for 1.2 crores or something, right? So that is one kind of a regression problem. Again, if the number of bedrooms are decreasing, obviously the price will also decrease, right? It can come to like 80 lakhs or something. So that is a regression problem. The other one is stock price. Based on the market value and all of that, your stock price might increase or decrease, and that is also a regression problem. Is the regression clear? You can either react or say yes in the chat box or anything. Cool. Thank you. So yeah, let's take the example of the house rent prediction, right? So these are some of the features that we are seeing. Let us say we have the location. So the location also plays an important role, right? So when you are going to buy a house, for the same kind of a house which are in two different areas, you will see a huge difference in the prices, right? That is the overall thing that you usually look at. And the size of the house and the area that it covers and transportation. Whenever there is an ad related to a real estate thing, they will say it is like these many kilometers away from a hospital, these many kilometers away from a railway station, and things like that. So the closer the accessibility is, the higher the price you will have, right? If your house if the house that you want to buy is closer to all kind of amenities, then obviously it is going to be higher, right? And yeah, is it furnished? Is it semi? It's not furnished or semi-furnished or fully furnished. If the house is fully furnished, the prices will be too high, right? And the utilities and if the pets are allowed or not allowed, and all of them. So these all are independent features. They are not depending on each other. Okay. So now I'm taking all of these independent features and I'm giving it to a model. So this is the black box to me now. Okay. I don't know what this model is doing. I'm just giving some output. Okay, sorry, I'm just giving some inputs and I want an output. That output is going to be what will be the rent or what will be the price. Rent or price. It can be anything. It can be like 1.26 crore or anything. Okay, based on all of these independent features, your the model is predicting something. So this prediction is a dependent feature because this is depending all on all of these independent features, right? So when one of the independent feature changes, the dependent feature, that is the rent or the price, also might vary, like it might increase or decrease. Okay, I hope this part is clear. Yeah. So again, in regression, we have multiple types. One is univariate, the other one is multivariate. Univariate means you are just taking one independent variable and you are giving some output. So if you look at this example here, the only variable that you're taking is how much of square footage is there in the house. Okay. So I'm saying it's 1500, 1800, and things are just varying, and then we are assuming then we are predicting the house price, right? So if you can see for 1500 it's 2 lakh 50. For 1800 it is increasing by 30K, right? So as the square footage is increasing, even the house price is increasing here. Okay, so this is just basing on one independent variable. I am having one dependent variable. So this is called as the univariate. If I have more than one, more than one independent variable, and in case if I have multiple dependent variables also, then then that is called as a multivariate. Okay, so in this example, I'm taking the square footage. Along with that, I'm taking how many number of bedrooms are there. Okay, so that is a second variable. That is a second independent variable that I'm taking into consideration to get the dependent variable that I want, right? So that is a multivariate regression type. Is univariate and multivariate clear? Okay. If anyone is not clear, please let me know beforehand so that then and there itself I can repeat. Okay, thanks. Okay, and that these are just one types of regression types like univariate and multivariate. And then there is another type of regression type. Okay, so the one is linear and non-linear. So if we are taking the relationship between a dependent variable and an independent variable, and if it is a straight line, then it's a linear. If we are having a linear function, then the regression type is linear regression. If it is not a linear, uh, not a linear graph or a linear line, then it is going to be a non-linear one. So, for example, if I'm taking the house prediction, okay, so let's say this is number of bedrooms and this is my price, right? So 2, 3, 4, 5, and 6. So I can say the starting point is maybe 50 lakhs in rupees. Okay. So if I'm having two bedrooms, then I might say I might put a price on this house for 50 lakhs, right? If I have three bedrooms, then I might increase a bit. So like that, I can go. Okay. So this is just an example. It does not necessarily have to be this way. So I'm just giving this as an example. So this is some sort of a linear graph. For example, if I say we are taking population across time. So maybe let's say in 2005, 2006, and 2007. um, You can take any kind of a thing here. Okay. In million or billion. Let us say in 2005, I have in India, there are these many number of people, and then we have these many number of people. Maybe let us say in 2007, it has decreased a bit, and then it has increased. So maybe it is like something like this. This is definitely not it's not a linear graph, right? So then I can say it as a non-linear regression. Cool. So these are the other types of regression types. So I hope both that all the four types of regression types are clear. Okay. So okay, now you might think we have independent variables, we have dependent variables, we have all of these, but how exactly are we going to predict what we want and what we don't want, right? So for that reasons, we have some regression methods. Okay. For linear type of regressions, there are different kinds of methods, and for non-linear, there are different kinds of methods. But for this class, we are going to discuss about ordinary least square regression. Okay. So ordinary least square, we also write it as OLS regression. So it is a kind of a statistical method. Okay, it's kind of a statistical method that is used to estimate the unknown parameters in a linear regression model. So the unknown parameters here can be the outputs. Okay, so we are going to predict something and we want to know. Okay, before we go into that, I have to discuss a equation. So I will discuss about OLS in the later slide. Okay, yeah. So for every problem, there is a procedure that we need to follow to get the output that we want. So how exactly are we going to do it? Again, so this is the entire flow chart for regression, right? Let's take the example of house price prediction again. Okay. So first we need to formulate the problem. So in the formulate the problem means you have to choose what kind of variables that you want to take. Okay. So what variables are we talking about here? Uh, Anyone wants to answer what kind of variables we can take into consideration to get some house price predictions? To one example, I can give number of houses, or another example is the square foot. What is a square feet of the house? Location, yeah, location, number of bedrooms, and square feet. Anything else? Awesome. Pool, water, yeah, square feet, bedrooms, safety. If it's a relatively safer area, you would not feel bad about spending a bit more. Transportation, yes. So, okay. So these are all some types of variables that we can take into consideration, right? So these are first we will set what kind of variables we want to take. For example, we might have even more than this, but we are not going to take everything. Okay. So sometimes some people may not give preference to a pool. Let us say, for an example. So I have to decide on what kind of variables I want to take. I'll say maybe I just want to take two or three into consideration. I'll say location, some bedroom, number of bedrooms, and transportation. Let's just say these three things I'm taking, right? So uh, I'm choosing what kind of variables I want to take. Out of all the variables I can have, I'm just choosing a couple of things, right? So that also you need to do. And then you want to take which model you want. So as we were seeing earlier, this black box which is there, you also have to choose what kind of a model that you want to take. Okay, is it a mathematical model, or is it a neural network, or a machine learning problem, or if it's a machine learning problem, what kind of a model you want to take, and all of that, right? Other things are also there, like method of fitting and some specific assumptions. So that we will see a bit later. Okay, but to give a brief, so model fitting is a process of adjusting whatever parameters that we are taking to match it best to the given data that we have. It's like if you are going to a tailor, you are going to get a suit that is going to fit your body right, right? Well, in the same way, the goal here is to create a model that will accurately represent the underlying patterns and relationships in the data. So it is the model is going to fit exactly to the data that you're giving. Okay, so that is method of fitting. And specific assumptions. So some assumptions that you are going to make, for example, whatever data I have, the mean is not going to be equal to zero, and things like that. Okay. Um, hmm. Then yes, once you formulate the entire problem, like what you want to do, what you want to take, and everything, then you fit the model. So you use this method called as method of fitting, which I was telling here. So the same thing that you use, what you have already decided upon. So you take that, you will fit the model, and then whatever assumptions you have made before, that same assumptions you are going to do here, right? So these are some of the things that we will cover also. So residual plots. So, okay. So let us say I have some data with me and I'm giving some x as an input and I am getting y hat as my output. Okay. But I have a table which is in between x and y. If I'm giving x1, I should get y1. If I'm giving x2, I should get y2. Right? I have this model black box, right? Sorry. So now I'm giving x1 as an input. My model is telling me y1 hat is the output. So there will be some difference in between what the model has predicted. What is the true value? The true value here is y1. Y1 minus this whatever prediction the model has made. So that is a residue, right? So similarly, you take all the residues into consideration and you will plot something. Okay. Why and what we will see later. Okay. And another one is outlier detections. So if I am having a graph, right, and I want to have a line that is going to fit the model everywhere, let us say, this is the data, but there are some data that are like way too away from the model, which is making the average go high or low. What is the difference between y and y hat? Y is the true variable, y hat is the output that the model is predicting. uh, I will explain that 1 second. So let us say we have a data set, okay, x1 y1, x2 y2, x3 y3, so on till x500 to y500. Okay, we have some 500 types. Out of this, I might take some maybe 400. 400 vari 400 pairs I will take for training and 100 pairs for testing. Okay, so this is the black box, right? So if I am giving x1 as an output and the model is giving me y1 hat as an output, so this is the predicted value. This is input, this is true value. So for a given value of x1 in real life, I should get y1 as the output. Okay, so if I'm taking this x1 and if I'm giving as an input to the black box, the black box is predicting y1 hat as an output. So there is a difference between this y1 hat and this y1, right? So this y1 hat is predicted and y1 is true value. Both of them will have some difference, right? So that difference, we call it as a residue. The difference between these two. Okay. I hope this is clear now. Okay. So let's get back to the other one out here. Let us say it's not exact, it's not zero. We cannot say it can be zero if the model is like 100% accurately trained. And I like that is like in a hypothetical situation, the model will predict what we can get in the real life scenario. So again, if you're taking that house prediction problem, if I'm saying if it's a 2 bhk and with a swimming pool, I might say okay, I'll give it for some 80 lakhs or something. But the model may predict 80 lakhs or it might predict 75 lakhs also, right? If the model is predicting 80 and if I'm also thinking of 80, then the residue is equal to 0. The difference between the two is 0. But if I'm thinking 80 and the model is telling 75, then the residue, the difference between both of them is going to be 5 lakhs, right? So in a real case scenario, we cannot say that it is going to be 0 all the time. It may give, give us 0 sometimes. Okay. So let's get back to outliers. This is some a problem that we have seen in a school or something. So we will be given some random numbers like this, and we'll be asked to calculate the mean of it, right? So let us say for all of these five values, I got a mean of mu1. Okay, so I'll say okay, these are the values. Then I'm going to add some other things apart from another number, which is going to be 799. Okay, then I will get some mu2 as my output, as my mean, right? Because of this value, which is almost close to 800, the mean is going to increase drastically, right? So if I'm going to plot all this, let's say 25, 30, 35, 40, 45. I have 140. I have a 45, I have a 30, 25, 23, 22. All are here, right? Um, I should probably change the direction like this. It's not happening. So sorry. I will redraw this again. Okay. Let's just say the first one is 25. The second one is 30. The third one is 45. The fourth one is around 23. And the fifth one is 22. Now I'm adding something called as 799, which is way too up, right? Somewhere here. If I'm taking the mean of only these things, then I might have the mean somewhere here, if this is the right point or not. I'm just kidding. Okay. Maybe new one is here. Maybe. When I consider this 799, then the new value will increase by a lot, right? So this is my abnormal data. This is called as an outlier. Because of this, the mean is increasing way too much, which is like completely away from us, right? And which is also in turn affecting the parameters that we are taking into consideration, right? So for a best case scenario, it is better if we remove this outlier completely. Okay. So I would like to show an R function, R code, to visualize it much clearer. Outlier can be understood as those who lie out of the curve fitting. Yes, absolutely. So I'll share the same thing. Just give me a second. Is it visible or not? Hmm. Can someone confirm if it's visible or not? Open. Okay. I don't know, for some reason I'm not able to see in my device. Okay, cool. So these are things just giving, you don't have to see that part. Yeah. So I'm just having some 1 to 100 values. Okay. I'm just having 1 to 100 numbers as 100 points. And these are going to be my independent variables. That's my temperature. Okay. As an example. And then I'm saying this pressure is going to be my dependent variable. Okay. So, and the function that is going to be is y is equal to 3 times of r norm into 100 and all of this. Like, just consider this as some mathematical expression. Okay, y is equal to 3x plus something. Okay, so we are calculating y as well. Okay, we have got these values. If you can see at the environment side, we have x values starting from 1 to 100, and y we are calculating based on. Is it not audible for everyone? Uh, yeah, cool. Okay, thank you so much. Okay, where was I? Yeah. So we have taken the x values from 1 to 100 and y values we have calculated based on this function y is equal to 3x plus r now. And then I'm just randomly introducing some outliers. If you can see here for y values, you have some 2.6 and all of that. And now I am adding some outliers. Okay. And then I am creating my entire data set. Okay. So I have a data which is having x values, y values. To the y values, I have added some outliers as well. Okay. And those outliers are there, and I'm going to plot and I'm going to show you how those outliers are there. I don't think this will be visible. Just a second, I'll share my entire screen. Okay, so the bottom one is my X data, that is the temperature data, and the left side, like Y axis, is my pressure data. And all the points that you see at the top are my outliers. I have added some random values. So these all are at one place, right? All the other points are at one place. But these are away from that lines, away from those points. So these are something that I call as an outlier. Okay. So how do I remove that? Okay. So, but before that, I want to fit a linear regression model. Okay. And these all, okay. And then I'm going to plot. Okay. Let's look at the image. Yes. So with outliers, along with the outliers, this is the line that is fitting my uh, x and y axis together. Okay. Based on this y is equal to mx plus c, that kind of an equation that I'm having right now here, right? So this is with outliers. So now I want to remove outliers. Okay, I'm removing the outliers. I'm just taking the data and I'm removing the outlier indices, and then I'll have a clean data. Okay, I'm fitting another model for the clean data, and then I am plotting it again. Okay, I'm drawing two lines. So the first line is the line that I had when I had outliers, which is red in color, and the other line, which is green in color, is the line which I'm going to have when the outliers are removed. If you can see this plot now, there are no outliers anymore. I'm just having the clean data which is close by, and the green line is after removing the outlier. This is the graph that I'm having. This is the linear line that I'm having, and this red one is the one this red one is the one that I'm having with outliers. Like when the presence of outliers, this red one is the one that was have, right? So this is between this is the difference. This is the reason why we remove outliers to fit the model. How can I draw the line? Yeah, we will see that as well. We will discuss that. I just wanted to show you what outliers and all are. I'll discuss about that. There is a lot of theory behind it. We'll discuss how we can identify the outliers. So basically, outliers are the values that are going to be like too much different. So once you plot all the points between x and y, it will be really clear for you above at the top you will always find them just like how we were seeing in the previous plot, right? So then you can what you can do is you can put up a threshold value. So here I can say in this graph, if you see, if I say if the pressure value is above 300, I don't want. Okay, remove all the points that are above 300. So then I'm going to eliminate some kind of an outliers. So sometimes we have to be also careful that we are removing the data that is useful for us. That is also something we have to keep in mind. Okay, unique values are outliers, not necessarily. um like it will be like too much away from the data that you're already having. It's easier to visualize uh, than calling it as unique, because sometimes we might have two outlier values having the same numbers, like maybe 799 and 799 twice it might come, right? Yes, like 799. Not able to open here. Just give me a second. But outliers can be resulted out of some anomaly. Isn't it important to understand the cause of? Yes, it is important to understand the cause of the anomaly as well. So that is why we also do data pre-processing. So that is not something that I'm going to cover in this particular topic, right? So before we take in any kind of data, we have to do some data pre-processing and all of that. Okay. So that is when you start asking your questions like, why is this happening? Why is this not happening? And everything. Okay. 1 second. Okay. Let's see. Okay. Um. Yeah. Regression illustration. Okay. So we have this multiple images. I mean, multiple points, right? So here we have multiple points. But how do we know how to plot this graph? So, like, many possibilities are there for us to draw the graph, right? It can be in this way, or it can be in this way, or like this, or things like that. But how are we going to know which one is the right line for us? Like, how exactly are we going to find? So, this is an example where we have a data set for a car service center where the x axis is the total number of cars that a service center has, and the y axis is the number of service minutes. So, how many minutes that it can provide service for a customer or something, right? So we want to find the best functional relationship between both variables, which can be given by a linear line, right? So we'll have multiple lines, and how are we going to find? So one way is like that's the main way. We are going to take the each point, and we are going to draw a line parallel to y-axis. Okay. So these lines are going to touch the some linear line that we are considering at some point, right? And things like that. Here and there. So what we are going to do is we are going to calculate the error in between. What is the true value? This is the true value, which is y, and this point is the y hat. Okay, this is something. This line may be something the model has predicted, so we are calling that as y hat, and this is the true value that we are having. So the difference between this y and y hat, we'll take that is called as an error here. We are going to take in all the errors across all the points, and then we are going to take a line which is going to fit the best among the with the data that we are having all together. Okay, just give me a second. I'll leave and join. Just a second, I'm not able to see any of your messages. Just give me 1 second. It's better if you guys can take a 5 minute break. I'll try to figure out what is wrong here. Okay. Just take 5 minutes break. We'll be back by 6:50. I'm sorry, I have made a mistake and I have left the chat and I have no clue how to get the chat back. But please post your questions in Q&A option for today. I'll try to figure it out by next class if possible. Okay. The Q&A is there on the top if you can see next to the chat box. Please drop your messages in Q&A. I'm not able to figure out what is wrong. Okay. Or if anyone knows how I can join in the chat, please let me know in the Q&A. Okay, any kind of conversation that you want to start, please write only in Q&A. I have by mistake left the chat and I have absolutely no clue how I can get it back. I have left and come back 3 times already, but it's not working. Okay. Um, so perhaps I'll try one more time. Just give me a second. Okay, for today it's just the Q&A. Please ask your questions on click. Try to click on chat icon. I tried. No. So by mistake I have left the chat and then now I'm not able to open it again. Like it's just saying I'm no longer having access to chat for some weird reason. If you do and clear the new teams, this is one of the suggestions. Okay, let's see. Okay, it's fine. For this class, we'll just continue with this Q&A thing. From by next class, I'll try to fit everything. Okay. Um, so sorry for that. Share my screen. Okay. Okay. So this is the point which we were discussing, right? Okay. Yeah. So we have a line, and then we are going to take the error in between the real points and the point that lies on the line, the linear line that we are going to take, right? So these things that we take into consideration, and then finally, whichever one is giving us the less error, we are going to take that as the linear line that we want, and that is going to be the relationship between both the variables. Okay. Uh, for now, as an example, I'll share the screen. Okay, we'll discuss about. I don't think this is sharing. Share screen. Okay. So we'll take some values. Okay, some random value data that I'm taking. So x starting from 1 to 6, I'm taking, and then let me just clear everything off here. Here. Okay. So x I'm just taking as some values from in between 1 to 6, and then I'm taking y as 3, 5, 7. These all are just like random numbers that I'm having. Okay. So with both of these together, I'm calling that as my data set. Okay. And I I use this function called as LM. So LM is linear fitting model function, which is going to fit a line, a linear line that is best suitable for the X and Y data that we are giving. Okay. So I'm just calling LM, and then what will be my Y axis, what will be my X axis. Okay, and the data. So we give the data set like this. Okay. Uh, yeah, and then we are going to print the model. So it is going to give me these values. Okay, first it is giving me residuals. if you can see, I have given total of 6 numbers, right? So these are the 6 numbers that I'm getting, and these are my residues that I'm getting. Residue is nothing but y minus y hat. Okay. So I'll have some residues. You will be clear once we plot it. So I'm plotting x and y. So this is my x and y, right? This is my x and y. And then I am drawing a line which is the accurate fit according to the model. Okay. So this is the line, right? Now, if you can see near this third point, the third point is a bit away from the line, right? So the y value is something close to 6, say maybe 7, right? And uh, maybe this can be somewhat around 6.2 or 3 or something like that. I'm not sure what is the exact point, right? If that's the third thing, the difference between the actual value of this point, which is almost close to 7, and then this point is equal to 0.37. Like that, this line is having different values at every x value, and then we are having the residues at each and every point. Okay, so far clear? You can just react. That's enough. Able to load. Can't solve problems. Okay. We'll see some problems. Okay. And then this line can be written as y is equal to mx plus c. C is nothing but the intercept and x values we have. And this summary of the model is going to give us all of these things, like what is the standard error, what is the t values and the probability and all of that. For now, you don't need all of these things. Okay, but later at some point, if you are doing much more deep analysis, then these all things will be useful. Okay, I am only just showing this for this particular graph, right? Yeah. Oh, I'd like to share this one. Hmm. Okay, so now, as I have told previously, that to solve a linear regression type of a problem, one of the methods that we follow is ordinary least square, right? So we also call it as OLS regression. So it is a statistical method used to estimate the unknown parameters in a linear regression model. Okay, so uh, as you can look at this line, the linear line, you can write it as y is equal to mx plus c, right? But we are going to have a different annotation apart from y is equal to mx plus c. Okay, so I'll call this intercept as v naught. Okay, and the slope of this as b1 cap, b naught cap, and b1 cap. And this is going to be my formula, my equation, the linear equation for me. Y1 hat is a predicted value, is a prediction. It's not being shared. So sorry. Okay, I'll start again. I'm so sorry, actually. I don't know what is wrong today. Okay, so the equation of the line that you have is usually we'll write it as y is equal to mx plus c, where m is the slope and c is the intercept, right? So in this problem, we are going to do something similar to it, but we will represent this intercept as, sorry. Okay. So this I'm going to call it as my intercept b naught cap, and the slope of this line I'm going to call it as b1 cap. Okay. So with these values, I have this as my equation, where y1 hat is the points on this. So this line is represented by this. Okay. Y1 hat are the points at this on this line. Okay. And this is my x values and this is my y values, and y1 values are y cap values are on the line. Okay. So if we are going to write the linear model, I'll write it as y1 is equal to b naught, which is the intercept, plus b1 xi. B1 is the slope and xi is that at that particular point, plus epsilon I. Epsilon I is the error. So every model is going to have its own errors here and there, right? So epsilon I is the error at that particular point. So if I'm having 10 points, I'm going to have 10 different yi. I'm going to have 10 different xi, and I'm going to have 10 different epsilon I, right? Okay. So the main focus here is on the error. Okay. We take in the error. Error is the only dependent variable, and no, always remember error is not an independent variable. Okay. So I'm rewriting this equation in terms of epsilon I is equal to, okay, and this is the equation that we get. And the sum of squares of errors. So this is an important thing. So whatever error that we are having here, we are going to square it up. Okay. We square it up and then we find B1 cap and B naught cap. And that is by optimization techniques that we have seen in the last and the last before class, right? So this SSE is a statistical measure that quantifies the overall error between a regression model's predicted value and the true values. So true values are y and the predicted ones are y hat, right? And I can write the error epsilon I is equal to y minus y hat, right? So from this equation, I can rewrite it as y minus beta naught minus beta 1 xi, right? Am I right or wrong? So that is epsilon I. So which is nothing but this. Is this clear or is it a bit confusing? Cool. Okay. So now we have the SSE. Okay. Now the main problem that we have, the goal that we have is to minimize this SSE. So the main principle of OLS is to find the regression line that minimizes this SSE. Okay. So first we take some normal equations. So you all already know how we take normal equation. So we take partial derivations of SSE with respect to the regression coefficients here, which is B naught and B1. Okay, and setting them to equal to 0, and then we obtain some set of equations. So those equations are called normal equations, and then we solve those equations and we get the best optimal values to that is the minimum value of these SSC. So I hope you guys remember that from the previous classes. uh, Error is not always positive. The error can be greater than y or less than y. uh, or else I'll just remind me again when I go back to R to showing the R code from the previous example from all the 6 points that we have taken. I'll show you the residues where some are positives, some are negatives. Okay, just remind me when we go back there. Okay, I hope OLS is clear. Okay, these values you know how to find. You take this one, you'll do partial differentiation with respect to B1 and B naught, and then you equate them to 0, and then you will have a set of equations, and you are going to solve both of those equations, and this is what you'll end up with. Okay, B1 cap is this and B naught cap is this. In case you have not written all of these down, please write it down so that these formulas will be useful for the next questions that we are going to solve. Yes, I'm going to show some problem. So first I have to tell you some theory, right? So this is the theory and these are the equations or the formulas that you need. So you guys can write it down. I'll wait for a minute and then we can go to solving the next things. So after OLS, I'll also tell you the testing for goodness of fit, and then we will go to the problems. Okay. Uh, the recording class, if you go to NPTEL, on the left side, you will find problem solving session as one of the headings. If you click on that, you will have two things. One is a form and another one is a link to the Excel file. Okay, if you click on that, all the YouTube links will be there according to the week. So this is week 6. So next to week 6, you will have the YouTube recorded lecture. You can click on the lecture and you can watch it. Okay. I think it's better if I go to the next thing. Okay. So, yeah, we are going to do this testing of goodness of fit. So, goodness of fit means it's a measure how well our model, the regression model that we are having, explains the variation in the dependent variable. Okay. So, the dependent variable, which is y or y, the prediction of the dependent variable is y hat. So there will be some variations in between y and y hat, and uh, how well the model can explain this variation, uh, this goodness of fit is going to measure it. Okay, so there are different types of statistical tests that can be used to assess this goodness of fit, but we are going to look at R square test and adjusted R square test. So R square means it's a measure of proportion of variation explained by the model. And we directly calculate this R square value. And the interpretation is that higher R square indicates a better fit. Okay, if you can see here, this R square is going to lie in between 0 and 1, and 1 being good and 0 being bad. And the formula for R square is this: yi minus yi hat whole square. Sorry, 1 minus summation of yi minus yi hat whole square divided by summation of yi minus y dash. This y dash whole square, this is the mean of y. Okay, yi is the true value. I'm writing it again. Yi hat is a predicted value, and y dash is the mean of y. You have to take all the values of y and you take the mean. Okay, so the top one is the variability or the variability which is explained by this line, and the bottom one is the variability in y. So R square is completely about explaining the variation of the dependent variable y. Okay. Okay. So this is a formula for R square test. And if we are taking adjusted R square, so adjusted R square is for the number of independent variables. And uh, if you can see, this is the formula for it. It is directly we will calculate this R square dash value. And the interpretation is that higher adjusted R square value indicates a better fit. Okay, so especially when you're adding more variables. So here n indicates the sample size and p indicates the number of independent variables that we are having. So independent variables are x1, x2, so on till xp, right? So these are two types of goodness of fit, but we also have different types like F test and mean square error MSE, or root mean square error RMSE, and also we look at residual plots also. So residual plots we will look at the end of the session. Okay. So I hope everything is clear so far. Okay. Degrees of freedom is not for now. Okay. Yeah. Um, I hope you guys can answer this. In a linear regression equation, what does the slope, that is b1 cap, what does that represent? If you want, I can draw the graph x, y. If this is the line, this is the slope. b1 cap is equal to dy by dx. A, B. Any more answers? Okay, one person says A, one person says B. Any more answers? B. Yes. Okay. So we all know X means independent variables and Y means dependent variables, right? So let's see the first one, the intercept of the regression line, which is wrong. Intercept is B naught cap. The change in the dependent variable for a unit change in the independent variable. Does it sound like this? Yes. So the right answer is B, right? The slope coefficient in a linear regression equation indicates how much the dependent variable is expected to change for a unit change in the corresponding independent variable while holding other variables as constant. Okay. Yeah, A is B naught. But in the question, we have asked about the slope, right? Slope is b1. Okay. Yeah. So let's look at the second question. What does the coefficient of determination r square measure in a regression model? So what is the r square measuring for us? What are we measuring when we are choosing r square test? What is the measure of it? Any answers? Okay, one person says B. Any more? Okay. Yeah. So as we have discussed earlier, R square is the measurement of variability in the dependent variable, right? Measure of variability. So if we see here, the first option is accuracy of the model's prediction. We R square has nothing to do with accuracy, right? And then we have the proportion of variance explained by the model. This is true. R square is equal to 1 minus summation of y minus y hat whole square by summation of y minus y mean of y or a whole square, right? So which means it's a measure of variance explained for the independent variable, sorry, dependent variable. Okay. We have let's go back to our basics. Okay. First, what I want you guys to do is find the mean of x and find the mean of y. First, sorry. Find mean of x and y for this given data. 3.5 for x. Yes, that's right. 7.5. Yes. All of you are right. 3.5 for x and 7.5 for y. So mean is equal to sum of all the values divided by total number of values that we have, right? So this is okay. The second part that I want is the deviations. So the deviations means xi minus x dash. X dash is nothing but the mean. This is the mean. Deviation means, can you calculate for all? Like it's individually for each and everything. So the first one is 1 minus 3.5, comma 2 minus 3.5, then 3 minus 3.5, 4 minus 3.5, 5 minus 3.5, 6 minus 3.5, right? And for y, it is 3 minus 7.5, 5 minus 7.5, and so on. Okay, I'll straight away write the answers. I'll submit here. Okay, so minus 2.5, minus 1.5, minus 0.5, 0.5, 1.5, and 2.5, minus 4.5, minus 2.5, minus 0.5, 0.5, 2.5, and 4.5. Okay, so these are called deviations from mean. Okay, so we have calculated mean, we have calculated the deviation from mean. Next, what I want is covariance. Covariance. I want to calculate the covariance between x and y and the variance of x. Covariance formula was here somewhere. Okay, sorry, I did not tell what exactly what is. So uh, I hope you guys remember this part, beta 1 cap. So here Sxy is the covariance of x and y, whereas Sxx is the covariance of x. I hope you guys remember from here. Okay, from this part. And these two are the covariances. Covariance of x and y divided by covariance of x and x. I forgot to mention it when I was discussing this equation here. Okay, so what is this exactly? So which it is nothing but xi minus x dash into yi minus y dash and summation of all. That is for sxy. Okay, so the covariance here is equal to, if I'm taking covariance between x and y, it is equal to summation of xi minus x dash into yi minus y dash for I equal to 1 to 6 we have, right? I equal to 1 to 6. And sxx is equal to xi minus x dash into xi minus x dash, which is equal to xi minus x dash whole square, right? So also, oh sorry, and divided by n. Divided by n, with n nothing but 6 here. Okay, so this is the covariance between x and y and variance of x. Covariance of x and y and variance of x. So can any of you compute both of them and tell me the answers? You can take some time. We already have all the values from here. You just have to multiply and sum everything up and divide everything by n. Keep doing it. I'll be back. Any answers from anyone? 22.5 numerator. Okay. Uh, Let me calculate it as well. 7.5. Is it for SXY or SXX? No. It's- the numerator should be 30.498. 30.498 divided by 6, which is equal to 5.083. That is for SXY. Okay. And this should give 17.496 divided by 6, which is equal to 2.916. Okay. Um, yeah, someone has raised their hand. Please put your messages in the Q&A. I don't know. I'm not able to see the chat box at all. So you really have to help me out here. If you have a question, please put everything in Q&A. If you're having your answer also, please put it in Q&A. Okay. Uh, so let's keep this like this for now. Okay. Then let us calculate the coefficients. Okay. The coefficients here are beta 1 cap and beta naught cap, right? So let us calculate coefficients. So let's start with beta 1 cap, because beta 1 cap is nothing but SXY divided by SXX, right? So which means SXY is equal to 5 point. You are getting SXX, you are getting it as 0. Okay. It is nothing but minus 2.5 whole square. Uh, how exactly are you getting 0? We are having all values here, minus 0.5 whole square plus 0.5 whole square plus 1.5 whole square plus 2 plus 2.5 whole square. This I can write it as, since all our first three are negatives of the same values as the other three, and minus whole square is equal to positive 1. So I can write it as 2 times of 2.5 whole square plus 2 times of 1.5 whole square plus 2 times of 0.5 whole square. Right? Yeah. Okay. No worries. So first you have to square it up and then sum everything together. Okay. Then this will get lost. These are the final outputs. Okay. 1.743. No. SXY is equal to 5.083 and SXX is equal to 2.916. Okay. Okay. You can do it in your free time again. Okay. You can go back and you can do it again. And okay. Then we have to find the coefficients B1, B1 and B0. Okay, B1 is nothing but SXY by XXX, right? So we already have the values 5.083 divided by 2.916, which is equal to how much? And your calculator. 916 is equal to 1.743 approximately. Okay? Yeah, cool. Yeah, you're right. So this is my beta 1 cap, right? Then now I want to find beta naught cap, which I can get it from y cap is equal to beta 1x plus beta naught, right? So I can write beta naught is equal to y cap minus beta 1x. Okay. So this is the same even for mean values, right? So instead of taking all x and y values, I will just straight away take the mean values of x and y. Okay. So I can write beta naught cap is equal to y mean of y minus beta 1 cap into mean of x. Okay, which is equal to what is mean of y? 7 point something. 7.5. 7.5 minus 1.743 into how much is x dash? 3.5. 3.5. Can anyone calculate this? It come close to 1 point something. 1.3995. Okay. 1.399. We can just approximate as 1.4, right? We'll just approximate it. So now we have all the values like beta naught and beta 1. Those are the unknown values that we were having so far. Now we have got that as well. So we will write the equation beta naught plus beta 1 x. This is the equation that we have, right? So let us write y. So this is not hat. Y hat is equal to beta naught is 1.4 plus beta 1 is 1.743 x. Okay, so if we are going to plot the graph, this is 1.4 and the slope of this is 1.743 between x and y, right? Okay, so this is how we finally find the equation. In the beginning, someone has asked, how am I going to get this line? So this is how you get the line. Okay, so this is all well and good. Now let's do the R square test. I hope all of you have taken the R square formula. If not, I'll go back and I'll show it once again. This is the formula for R square test. So please note down if you haven't noted it down. But in case if you have noted it down, you can find the values. Okay. This is usually going to take a bit long. Okay, this you can do by yourself. I'll write it here. 1 minus, forgot it, sorry. Summation of y minus y hat whole square divided by summation of y minus y mean whole square, right? So you have y values in the table itself. You have the y values. To get the y hat values, what you are going to do is you are going to put x values in this, and then you're going to get the y dash values. Get y hat values from here, from this equation. Okay, from the table, what all x values you're having, put each x value here, and then you'll get the y hat value. you already have the y value corresponding to that particular x value, and you already know the mean of y dash, right? So like that, you can get the r square one, and also adjusted r square, right? So you can try this in your free time. We still have only 25 minutes left. So I just want to finish this off quickly as possible. Okay, so this r square should be equal to 0.9936, and adjusted r square should be close to 0.992. Okay, please do it later. Okay, in case if you're not getting these values, please drop a message in the Q&A in the NPTEL course lecture part. Okay, from there I will see and I will reply. Okay, so this is something that I wanted to show you guys. This is the same data from the table that I have given before. So we have all the 1 to 6 values across x-axis, and we have the y-axis values. And then I have pointed the data. These are the actual data. And this is the regression line that we have got. This is y hat is equal to 1.4 plus 1.743x. Okay, this line is this one. Okay, so this is the overall till here. Okay, okay, I'll go to our studio now. Stop sharing this. And I should probably share the entire screen. Okay. So we have finished the linear regression, the linear model we have finished. We have finished the outlier model as well. And I did not show you the multivariate linear regression problem. So when we are having multiple independent variables, how are we going to do? Right? So in the linear problem before, I was just showing a single, I was just taking x and y values. So now I'm taking two values, x1 and x2. Okay. So in a minute, I'll clear everything up and then show. So I'm taking 100 observations, and I'm taking x1 as my first independent variable and x2 as my second independent variable. And I'm also adding some error to it. And assume this is the true relationship. This is a true equation. Y is equal to 2x1 plus 3x2 plus error. Okay. In case of the single one, I mean, in cases of single variable, we were taking y is equal to 3x plus some error, I think. So since we are having multiple variables here, we are taking two different variables, 2x1 plus 3x2 plus the error as usual. Okay. So this is the error, and I am defining the function y is equal to 2x1 plus 3x2 plus error. Okay. And then I'm combining all of that into a data frame. Okay. And then I'm going to just display the first few rows of the data set. So here I have x1, I have x2, and y. x1, x2 being my independent variables and y being our dependent variables. I have total of 6 different variables like that now. Okay. Now I want to plot two different plots here. One is uh, x1 with y, and another one is x2 with y. Okay. So I'm plotting one. Hopefully this is clear. So this is the scatter plot in between x1 and y. And then I'm plotting a second one, which is in between x2 and y. Right? Any questions so far? Okay. So that is for these plots are for x1 and x2. So this is okay. Now I want to have a plot where I have both x1 and x2 along with y. So it is going to be my 3D plot, 3D graph. How we are going to have x, y, and z axis in a 3D graph that we usually make. Similarly, we want to look at x1, x2, and y together. Okay, so I'm setting up a new plot environment, and then I am calling a model that is going to fit y with respect to x1 and x2. Okay, and so this is a package that I'm going to use. Okay, for multivariate regression, linear regression model. So you can call this library, you can install this library. Once you install the library, you can just, you guys know how to install the library, right? So then I'll call the library RGL, and now I am going to fit the model. Okay, y tilde x1 plus x2. So this means y is my dependent variable and x1 and x2 are my independent variables. So y is depending on x1 and x2, and this is the data that, and take the data from this data set. Okay, so the model is done, and now I'm asking it to create a 3D scatter plot with some data points. Okay, so this is a 3D scatter. This is a 3D scattering plot. So as you can see, this is the y-axis, this is the x2, and this one is the x1. So based on that, we got a 3D plot. Okay. When we are having just two x1 and one independent and one dependent variable, it is just a 2D plot. We are just having a single line. Now, since we are having more than one variable, we are not going to have just a single line. We are going to have a regression plane. Complete plane will be there. Okay. We'll see. For that, we actually need to extract some coefficients for the plane. Okay. Uh, yeah, it will. Okay. So we are extracting the coefficients from the plane, from the model itself, and then we are going to label them. Okay. It's like ax1 plus bx2 is equal to c kind. Okay. And then we are plotting a regression plane. So this RGL function, the library has something called as planes 3D, and that is going to add a regression plane to the plot. Okay, so this is the regression plane. When we are having just x and y, we have a line y is equal to mx plus c kind. But when we are having more than one independent variable, we are going to get a regression plane. And this is the plane. Okay, you don't have to go deep into it. This is just for visualization purpose only. Okay. Yeah. So this part is done. I'll share all the R codes on Google Drive. You can take from there. Okay. And this is just a small example. Okay. So we have taken different kind of datas like 1, 2, 3, 4 random numbers we have taken to find some plots, right? So I'm taking a proper data set which is available on our studio. So which is a women data set. Okay. If I check what is this women data set, I have the height of women and the weight of women. Okay. I have their height and weight, corresponding height and weights. Okay. Calculating the summary of it. So this is the minimum value that I have in the entire data set for height. And this one is a minimum weight I have in the entire data set. So don't think this is in kgs. This is in LB. Okay. Uh, okay. So then I am going to plot the data set between height and weight. Okay. So this is a plot we had. And then I am calling the model. I'm adding a linear model to this one with the weight being the dependent variable and height being the independent variable. Uh, yeah. and then I'm going to print the model. It gave me the beta 1 and beta naught values. Okay. Huh. And then I'm plotting the regression line, and this is the line that I got. Okay. So this is just for an example sake that I have added instead of having just 1, 2, 3, 4 numbers and everything. Okay. Uh, Clear so far? For adjusted R2, what is the p value? P value is the total number of independent values, I think. Yeah, independent. Yeah, total number of independent variables. So independent variable is only one here. So you take p is equal to 1. Okay. I hope all are clear on this one. We are running short on time. So, okay. Okay. For the same thing, let us see. Okay. So for the same data set that I have taken earlier, 1, 2, 3, 4, 5, 6, and y is equal to 3, 5, 7, 8, 10, and 12. So will you be able to answer these things? The first one is, what is the slope coefficient of the best linear regression line for this data set? How to arrive at that conclusion? Like, is it best or not? So when you are finding the formula for beta 1 cap, so what we were doing is we were trying to minimize, like we were trying to optimize the error value, right? This sum of the squared error, SSE. Regarding P, okay, that's a really long derivation to go. Regarding P, what you can see. So if you are interested, you can look at the derivation for that alternative r square. Okay, sorry, adjusted r square. You can find, and in this particular example, we are having just two variables. One is x and one is y, and based on x, we are finding y, right? In this entire example, so y is something that we are finding, which means it is a dependent variable. It is depending on x. Okay. And we don't have any other variables. X is an independent one. Y is depending on x. So we just have one dependent variable and one independent variable. And that is how we come to a conclusion that p is equal to 1 in this particular case. Right? Sorry, I think I have given the wrong values here. Apologize for that. I apologize for that. Let me just change some values. 8, 7, 5, and 11 only. Okay. Uh, can you calculate the slope for this one now? Can you calculate the slope for this one? Uh, all of this is going to take quite a long time, I guess. Okay. Since we are running short on time, uh, you can try this in your leisure time. Okay. Okay. All of this is easy. Okay, I'll just say beta 1. This is beta 1 cap. You already know the formula for it. right? You take the covariance of xy and variance of xx, and you will find it. We have done it in the last one. And beta naught, also you know how to do it. You take the mean of y and mean of x, and you also take the beta 1 cap, and you will find the beta naught, right? And what is the predicted value of y when x equal to 6? So once we get the equation here, you take the equation here and put x equal to 6, and beta naught and beta 1 you already have. So you will put the values and you will get the predicted value of y. So which is y hat, right? Um, okay. And yeah, R square formula you already know, 1 minus variability of yi and y hat divided by variability in bit of y with respect to the mean of y, right? R square you already know. And mean square error, this was not discussed. So mean square error is equal to the y minus y cap whole square divided by n. Okay, so y minus this is nothing but the residuals whole square divided by total number of data points that you are having. Okay, so that is the mean squared error. If the slope of the linear regression line is 3 and the intercept is 2, what would be the predicted value when okay, so it is given what b naught is equal to 2 and b1 is equal to 3, x is equal to 8, y is equal to beta naught plus beta 1 cap x, right? So beta naught is equal to 2 plus beta 1 is 3 and this is 8, and you will get your answer. Okay. Uh, so far clear? So apart from that, there are some other quantities that I wanted to discuss, but we are running a bit short on time. Okay. So one is sum of squared errors. So you are going to take all the residuals and you are going to square it up. Okay, so that is SSE, right? So okay, and then you have some this y hat minus mean of y whole square, which is called residual sum of square. Can you explain the difference between covariance, variance, and covariance? Variance means you are showing the variance of one particular variable only. If I'm saying variance of x, it is sxx, okay, which is nothing but x minus x dash whole square. If I'm talking about covariance, I'm taking two different variables. One is x, one is y, which is equal to summation of x minus x dash whole square into y minus y dash whole square. Okay, so that's the difference between variance and covariance. Yeah, yeah. So we have SSE. SSE means the true value minus the predicted value whole square and the summation of all the data points. Okay, and SSR is the residual sum of squares. So whatever predicted value that we are having, we are going to remove the mean of y and then we are going to square it up. Okay, these are some kind of definitions that you can follow. Okay, sometimes they are useful to find some things. Okay, and SST is the total sum of squares. So this is something you already know. Y minus y, mean of y whole square. So that's the variability of y, and okay, variability of y. Okay, and this is residual whole square. Okay, and the relationship between these three is given by SST is equal to SSE plus SSR. Okay, you can take a few examples and you can try to prove this also. Okay, that is also possible. And you can also write r square test in form of 1 minus SSE by SST. So you already know what SSE is. It is this, which is variability of prediction with respect to y, of with respect to true value. Okay. So 1 minus variability of the predicted value divided by the variability of y, right? Is that the same as r square that we have discussed earlier? Okay. So if you can note down these formulas, we can solve a couple of questions based on that. Is it okay if I take 5 minutes extra, maybe like 8:05 or 8 till 8:05 or something? I need to cover hypothesis testing and as well. Okay, cool. Um, okay, since that is fine, I think uh, since I'll share this one, you can try the questions out yourself. So it is not that hard. I'll also write the explanation at the bottom, okay, so that it will be clear for you. Okay, so next step is just a second. Okay, so then the next step is hypothesis testing. So we had briefly looked at hypothesis testing in one of the previous classes, right? So this is hypothesis testing on the regression coefficients. So initially, like previously, when we were looking at hypothesis testing, we were saying we had two types, null hypothesis and alternative hypothesis. And previously, we were saying in null hypothesis, the mean is equal to this much value, and alternative hypothesis is the opposite of that. Mean is not equal to this value, right? So similarly, in this hypothesis testing also, we are having we are uh, making a hypothesis based on beta 1 or beta naught. Okay, most probably beta 1, based on the slope. Okay, so in this case, the null hypothesis that I'm saying is beta 1 is equal to 0. Okay, then the alternative hypothesis is definitely going to be beta 1 is not equal to 0, right? So we know y hat is equal to beta naught plus beta 1 hat of x. When I say beta 1 is equal to 0, this is going to become 0, right? And some epsilon, some error. Then y hat is equal to beta plus epsilon if null hypothesis is true, right? So from a larger model, it has reduced to a smaller one, and hence we call it as a reduced model. Okay. In case if the null hypothesis is true, then we get a reduced model. In case if the null hypothesis is not true, then we are going to have the entire equation as it is. So hence we call it as a full model, right? So this hypothesis testing is in order to check if the linear model is a good fit or not, and we can test whether this estimate of beta 1 is significant or not. So when you there are different types of tests. One of the example is t-test. Okay, if you do a t-test, it will tell you if your null hypothesis is right or wrong, and it will also give you the significant value also, significance also. Okay, so that is like going too deep, and we don't want to go too deep into all of that in the beginning stage. So for now, just know what null hypothesis is and what alternative hypothesis is and what gives what kind of models. Okay. Um. Yeah. And This one is something that you have seen in the R code that I have shown previously. If you take a summary, you will have this estimated standard error of x intercepts and x intercept and the x1. X1 here. Okay. Mm, so now we can just go to another one. Okay. And this is a residual plot. Okay. So in the first data set, if you see, we are having the x1 as one on one side and residual on the other side. Residual is nothing but y minus y hat, right? So I have these values and every thing is scattered here and there, right? In the first data set, in the data set one, all are scattered here and there. So there is no pattern that the residue is falling. Okay, it's a random one. Okay, so if it is a random, no patterned one, then we call it as a valid model. Okay, when we are having a plot that is a random one, it is a random, it is a valid model. So in case if we are taking a different kind of a data set and if I'm finding some pattern like this is one pattern, this is one pattern, this is one pattern. Here and there we might have some outliers, but that's okay. But in case if the other data which is there is following a pattern, then we say that the model is not a valid model. Okay. So that's it for residual plots. Okay. Um, that is all for today. Thanks for joining, everyone. Um, how we expect questions in final exam? Is it sufficient? Um, okay. Um, I may not be the right person to say anything about the exams because I'm not the one who is going to set the question paper. Okay. I suggest you go through the lectures and finish all your assignments, and it should probably be enough, at least according to me. Okay. Um, degrees of freedom and confidence intervals will be like it will be coming in the next in one of the 2 weeks, the seventh or eighth week. Okay, then we will cover it entirely. Okay. Yeah. Thank you so much. Any other questions? Degrees of freedom and confidence intervals will be. I'll have a separate part for it. Okay. Okay. If there are no questions, I'll probably end everything here. Okay. Thank you all for joining and have a good weekend. Bye.